Hello and welcome back to another lecture. In this lecture we're going to go ahead and compute the pre-stresses in simply supported double T-beam. Take a look at the problem. A simply supported pre-tension 70-foot span made from a lightweight concrete, steam cured concrete, and it has about 12 half-inch diameter strands in it, which is 270 Kips grade. And also the eccentricity as shown on a board, you can see is in the mid span is about 18.73 inches, and at the end is about 12.98 inches. So we want to calculate the losses at the critical section, which is about 0.4 times L, and also considering at the different stages, stage 1 at the transfer, and after then stage 2 after concrete topping is placed, and then take a look at it 2 years down the road. All the design criteria and information, as you can see, is given to us. F prime C is 5,000 psi lightweight concrete, and the F prime initial curing is 3,500, and then has given us 615. The moment inertia has given us 59,720 inch, and you can see the C bottom and C top is given as the C bottom is given as 2198, which is the maximum, and C top is about 10.02, and section modules also given. We have more information on the second page, and those are right here, as you can see from the shape. And the loading condition is given. The W dead load, not including topping, is 491 pounds per foot, and W 2-inch topping is 250 pounds per foot, and life load is 40 pounds per square foot, and FPU is 270,000 psi. All right, so let's get to work. First thing we're going to calculate is the module of elasticity, initial module of elasticity when they pour the concrete. So ECI is equal 33. And we had the equation right here. Weight of the concrete by power of 1.5 times square root of F prime C, which is initial setting. So that comes out to 33 times the unit weight of the concrete was given to us as 115 pound concrete, and that by power 1.5 times square root of the initial setting of the concrete was 3,500 psi. So that comes out to 2.4 million psi. At the same time, we want to calculate the module of elasticity after the initial setting and after 28 days curing. So that's going to be EC, which is equal 33 times, same formula, 115 by power 1.5, and time, and I think it was 5,000 pound concrete. So that's equal 2.88 million psi. We're going to look at the stage 1 transfers. The question is asking calculate the losses at the critical section, and we were told the critical section is at 0.4 times L, and L is 70, so 0.4 times 70, that is equal 28 feet. And of course we have right here, let's get this and blow this up a little bit here. If that's my neutral axis right here, or center of gravity, and then we have the strands coming down like that. I'm just doing it from here, half of the triangle right here, and this distance was 1298, and then this distance from here to here was 1873, And remember, this distance right here is 0.5 L. We want to know right here, which is a 0.4 L, that's critical section. We want to know what is our E at this point. So we're going to calculate E right here. So basically, we're going to, the ratio of the two triangle 0.4 L divided by 0.5 L, that's a 0.8. And we're going to go ahead and say 1298, our E is equal 12.98 plus 0.8 times 1873 minus 1298. And that gives me 17.58. The thing we're going to calculate is the dead load moment at that point. If you take a look at the beam formula, with the dead load, it's going to become, let's write down dead load at 0.4 L, and the equation was MD is equal WX divided by 2 time L minus X. So our MD comes out to, we have 491 pound time X is at 28 feet divided by 2 time 70 minus 28. That comes out to 708 foot-pound. Let's convert this to an inch-pound, which is going to be equal, basically, if I multiply that by 12, it's going to come out to 3,464,496 inch-pound. So now we calculated the dead load moment at the critical section. That's what it came out to. Okay, so our initial pre-stressing steel comes out to 0.7 times FFPU, which was 189,000 PSI. Therefore, we're going to find out what is the compression load. And so our initial load is going to be the area times the FPI. And the area was, we had 12 strands, and they were half inch, and the cross-sectional area was 0.153 for each one of them. And if we multiply that by 189, it's come out to 347,000 and 4 pound. Now we're going to go ahead and calculate the stress in a concrete at the location which we talked about in the previous screen, at the location of critical load, which was 0.4 times L, and that's going to be that formula right there. So FSCS is equal minus PI, which is minus 347,000 4 pound divided by the area of concrete was 615, I believe, correct, and multiply 1 plus E, we calculated, come out to be 1758 square, divide that by radius gyration 97.11, and plus the due to the dead load moment, which was 3,464,496, multiply that by 1758, and divide the whole thing by moment inertia, which is 59,720. And that should give me minus 1,340 psi. So that is the stress in the concrete. Now we like to know what is the module ratio is, and so we can multiply that by the module ratio. And we said that the module ratio at the initial stage, EPS by ESCI initial, well, this was 27 million divided by the ECI, which we calculated, it was 2.4 million. So that comes out to 1162. And therefore, our loss is going to be, the loss in steel is going to be due to this initial stage, is going to be 1162 times 1340, which that will give me about 15,571 psi. So just let that write that down here. Initial stage is 15,571. All right, let me erase this board. We continue. Okay, so now we're going to go ahead and calculate the steel stress relaxation, and we knew we had all these from the problem was given to us, and we calculated this 0.70%, and that's given, and they said the transfers occurs after 18 hours. So we're going to go ahead and use this equation and to calculate the losses. That is equal, FAPI came out to be 189,000, and multiply by log of 18 hours minus log of 0. So that's going to be minus log of 0, so that 0 is 0, divided by 10, multiplied by FAPI 189,000 divided by 230, and minus 0.55. So delta FAPR comes out to 6,447 psi. This came out to 64. Let me write that down here. 6,447. And if we continue with creep loss, at this stage is 0 at the initial stage. So is a shrinkage loss. And that's also 0. So our total loss comes out to, for stage 1, which is the initial stage, and 15,571 plus 6,447. So that comes out 22,018 psi. So our pre-stressing is going to be reduced from so our FAPI at end of stage, at the end of stage 1, is going to be 189,000 minus 22,018 psi, and that is equal 166,982 psi. Next, we're going to move to stage 2, And stage 2 basically is after 30 days. Let me clean this up. So now we're going to come into stage 2, transfer to placement after 30 days. And we have the modulus elasticity after 28 days came out to 2.8 million, and for the steel was 28 million. So our ratio is going to come out to 972, and we had the stress in the concrete at the initial stage 1340. And the next thing we're going to calculate the the 2-inch topping. But you see, the dead load of that, what's the dead load moment? The weight is going to be basically itself. You have 2-inch divided by 12 times 10 feet. This whole thing is 10 feet. And the concrete, so the 2-inch concrete, it's not a lightweight concrete, it's a regular weight concrete that's 150 pounds per cubic feet. And that comes out to 250 pounds per foot. And our moment is, if we remember, MD comes out to, so our moment comes out based on the equation you see on the board, W times X divided by 2 times L minus X, which is basically comes out to 250, and X was 28, which was 0.4 times L. 28 divided by 2 times 70 minus 28, and that comes out to, let's multiply by 12, make it an inch pound. So that comes out to 1,764,000 inch pound. Calculate the stress due to the superimposed dead load, and that comes out to MSD times E divided by I. Basically, it's the MC over I, right? So that's going to be, moment came out to be 1,764,000, and E was 1758, and I was 59,720. So this is going to come out to 519.3 psi. We did all this to calculate the creep loss, and it's got an equation for creep loss is what we have on the board, and I'm going to write it down. It's in K. So now the K, if you look at what we have based on ACI, it says 2.0. However, because we're using lightweight concrete, we've got to reduce it by 20%. So that's a 2, and replace it by 20%, and that's make it 80%, so 0.8. So it's 1.6. This 1.6 is not the same as a post tension. There's a note at the bottom of it. So that's equal K is equal KCR. KCR. So now we're going to end up with 9.72 came out to be N multiplied by 1.6 times FSCS came out to be 1340 minus 519.3, and that is equal, you can double check my number, I get 12,768. So this is a creep. I'm going to put that down here. 12,768. It's after 30 days for the creep. Let me erase this board. We'll continue. So now we're going to go ahead and continue with this same stage 2, but this time we're going to do shrinkage loss. We have the relative humidity at 70%, and this is the equation you can all see at board. And we got to calculate first. Let's calculate the volume and to surface ratio. So we're going to go ahead and calculate volume to surface ratio. Basically is the area over the perimeter of this cross section. The area was given to us as 615, I believe. And the perimeter, if you measure it yourself, it comes out to 364. One thing you have to do, make sure this is a triangle and this length is a little bit longer than what they show in here. So this ratio come out to 1.69. Therefore, our losses for shrinkage is going to come out 8.2 times 10 by negative 6, and KSH for pretension member is equal 1. So to do that, our T1 is equal 18 hours. Our T2 was 30 days, so it's 30 times 24, and that comes out to 720 hours. And our FPS stage 1 is 189,000 minus 15,570 minus 6,447, so that comes out to 166,982. And so that equation, if you recall, delta F of PR is equal F prime F of PI time log of T2 minus log of T1 divided by 10 and multiplied by F prime. It should be a PI time divided by F of Y minus 0.55, which is equal. We have 166,982 time log of T2, 720, minus log of 18 divided by 10 time 166,982, divide that by 230,000 minus 0.55. Comes out to 4,702 psi. I'm going to go ahead and write this in here. The stress in the strands due to the additional topping is n time FSD, which we both have these numbers already calculated. That become 5,048. This is at additional stress. It's not going to be a loss, so it's going to be a plus. And since these are loss, I'm just going to type this one as a, just leave it here as 5,048. And let's put a plus in here. Those are all going to be a loss. These are not going to be loss. Now we're going to move to stage 3, which is end of 2 years. At end of 2 years, so our creep and our shrinkage is going to be the same thing. It's not going to move. We did it after 1 month over here, which we calculated all these. So those are going to be the same. It's not going to change. So we're not going to add anything else. And since both, the only thing really is going to be different is going to be the steel relaxation, and after 2 years. And that's going to be calculated our F of PE, which was 189,000 minus all those losses, as 22,010 minus 23,660 plus 5,048, and that comes out to 378. 148, 378, 148, 378,000 psi. And now we're going to use that number to calculate the steel relaxation after 2 years. And using the formula, I'm just going to go ahead and write the equation. Write the F of PR is equal, that number, 148,378 times log of 2 years. 2 years is going to come out to 2 years times 365 times 24, and that's going to be 17,520, 17,520 hours. So it's going to be log of 17,520 minus log of 30 days, because we already did that, so that was 720, and divided by 10, multiplied by 148,378 divided by 230, and minus 0.55. So that comes out to, you had 1947. So again, 1948. Total loss going to come out to our F of PE at stage 3 after 2 years. It's going to be 148,378 minus 1948. That is equal 6,430. 146,430 psi.